Math 265A, Quest to College. I'm Joe Vasta, and we are covering section 5.4, Integrals, Symmetry, Average Value, and Mean Value Theorem. Your book calls this section Working with Integrals. That's a little less descriptive, but this is what I'm doing. So let f be a function. This is a pre-calculus topic right here. You can check to see about symmetry with your function by plugging negative x in for x. If you end up getting the same function, then f of x is called even. And an even function has y-axis symmetry. If when you plug negative x into the function you get negative your function, then your function is called odd, in which it has origin symmetry. If you get anything else, then your function is neither even nor odd. So that is from pre-calculus. Let's go ahead and evaluate some integrals and see some properties with symmetry and some definite integrals. So here's our first problem here. And what we're going to do is we're going to use the fundamental theorem of calculus to evaluate this integral. So what am I going to do? I'm going to go ahead and write this as x to the fourth over 4. This gets evaluated from negative 2 to 2. And then I have what? I put 2 in there. I end up getting 2 to the fourth, which is 16 over 4. So that is 4 when I put the top one in. Now I'm going to subtract and put the bottom one in. This is also going to give me negative 2 to the fourth. So it's also going to give me 16 over 4, which is 4. I end up getting 0. So a few things to realize about this is x cubed happens to be an odd function. Now I'll go ahead and do that little test from the first page. If f of x equals x cubed, then you put negative x in, you end up getting negative x cubed when it's all done being multiplied, which actually equals your negative function, which tells you that f is odd, origin symmetry. Origin starts with an O, and so does odd. So what does the graph look like? The graph looks like this. Y equals x cubed. Looks like that. Here's x, here's y. We went from negative 2 to 2. And if you're looking at the net area, oh, my picture's not perfect, because that should actually be a little more symmetric, what I did there. You'll see that that probably has an area of 4. And then this blue one has an area of 4 as well. And what happened to the red and the blue? And I feel ashamed of this picture. It should be a little nicer. Those canceled out. The negative canceled out with the positive. And you ended up getting a net area of 0. So this happens with odd functions when you're integrating from like negative 2 to 2 or negative 5 to 5 when you have opposites there. So when you have opposites, this will happen where you'll end up getting 0. And so there's a shortcut, and I'll put some rules up in a few pieces of paper from now, where you have from negative a to a, and then this right here is an odd function. The answer will always be 0. And that could help speed things up when you're doing integration problems in this class and other technical classes. Let's go ahead and do another problem here. Maybe I'll approach this one a little differently. So this one right here, we are integrating an even function. Now how do I know it's even? So we'll call that f of x. Well, the algebraic way of testing to see if something is odd or even is we put negative x in for x. We end up getting the same function. So f is even, which means it has y-axis symmetry. What does f look like? Well, f looks like your standard parabola. Here's x, here's y, and yeah, this looks like that. Looks like that. Okay, so this is y equals x squared. We are integrating from -2 to 2. I do like this picture better than the last one I did, because those things look more symmetric here. And so let's just naively do this problem. I mean, suppose we didn't get into the fact that this was an even function. We just said, let's integrate this. We'd end up getting x cubed over 3, evaluate it from -2 to 2. Fundamental theorem of calculus, that's what we're doing now. We have 8/3 minus, we're going to put -2 in there, and we'll have another 8/3, but it's actually -8/3 because -2 cubed is still negative. And so this gives us 8/3 plus 8/3. Now really, in terms of the picture, what is happening here? This guy right here has an area of 8/3. And so does this guy right here. And so this is more like saying 2 times 8/3. Not that you have to write that. So our final answer is 16/3. So when you are integrating an even function from a negative number to its opposite, it's not going to be 0 like it was with an odd function. But what it's going to do is what we could have done. So here's the shortcut. So you could have integrated from 0 to 2 and picked up the area of, or the net area of the right-hand side. And then done what? Then multiplied it by 2. Okay? So these properties where you're going from like -a to a, they only exist when you have even functions like here and then the odd function, which was example number 1. So if you're going for, you have opposites there and you have something that's not even, it's not odd, then there's nothing you can do. You just have to do it the long way. So part of our title for this was integrals, symmetry, average value, mean value theorem. Well, this is the symmetry part. So let's go ahead and put up our little thing that we discovered with the last 2 problems. This right here. You're integrating from -a to a over an odd function. This is, forgot to mention one thing, and maybe you probably didn't have me for pre-calculus. An odd function is a function that is symmetric about the origin. It means if you turn it upside down, you get something that looks like the same function. Well, in any case, if you're integrating from -a to a over an odd function, you're always going to get 0. Now, if you're integrating from -a to a of an even function, you can instead go 2 times the integral from 0 to a of the even function. Now, why would you want to do that? Well, because it's easier to put 0 into functions than it is to put negative a into functions, as we will see when we do some examples. So this is what we kind of derived with some examples. And now we get to things that you'll see in your homework. That look like this. Use symmetry to evaluate the integral. Okay, so we have this function right here. Maybe off to the side you can do this. F of x is x minus 3x to the 7th. Some of you already know the result that will happen. We put negative x in there, and we end up getting negative x minus 3 times negative x to the 7th. So this is negative x. And then we have, well, this negative x to the 7 is going to become, I'm going to write the same thing. It's going to be negative 1 to the 7 times x to the 7. So this is negative x. This negative 1 to the 7 is negative 1. And we have another negative, so this is plus 3x to the 7th. And does that look like our original function? No, it seems to be off by a negative. I'm going to factor a negative 1 out. And there's our original function here. So we have just put negative x into the function and got negative f of x. Which tells you that this function right here is odd, has origin symmetry, and you're integrating it from negative 100 to 100, which means you're going to get 0. Okay? And a way you can remember that is that O looks like a 0. Origin symmetry. So maybe that's a way to jog your memory. Now, if this said from negative 100 to 150, then we couldn't do that. We couldn't just say 0, we'd have to evaluate it. I mean, there are little things we can do, but we're done with this problem. Let's go ahead and do another problem. Use symmetry to evaluate this definite integral. Okay, so what do we have here? We have x squared, and we know that that one is an even function. If you're going to look at this guy right here, the cosine of x looks like this, which looks like it has y-axis symmetry. So cosine of x separately is also an even function, and there is a theorem that says if you add two even functions together, you get an even function. We can go off to the side and label this whole thing f of x and plug a negative x into that function. You'll get the same thing here. So in any case, this right here is even. And so we're going to use the little shortcut, because we have opposites there, that we can go 2 times the integral from 0 to pi over 4 of, we'll keep the same integrand there. And now it makes it a little easier because we have a 0 there instead of a negative pi fourths, and we have the 2 out there because we're going to multiply that by 2. So let's go ahead and crank out this integral. We have 2 times. The antiderivative of x squared is x cubed over 3. And the antiderivative of the cosine of x is the sine of x. And so we have this. We're evaluating it from 0 to pi over 4. So we're using the fundamental theorem of calculus. I'm going to put pi over 4 in for x. So I have 2 times. Okay, and here we have pi over 4 cubed over 3 plus sine of pi over 4. Then we have minus, we'll go like this right here, minus Put 0 in for x now. See, this is a lot easier to put 0 in for x than it would be to put negative pi over 4 in for x. So we'd have 0 there, 0 cubed over 3 is 0. And what is sine of 0? Sine of 0 is 0. Let me just write out sine 0 here first. Okay. So this is really pi cubed over 4 cubed. 4 cubed is 64. So you have pi cubed over 64. And then this is a copy dot flip, so this is going to be times 1/3. Then we have the sine of pi over 4, which is 1 over root 2. This gets multiplied by 2. And then this guy right here, sine of 0 is 0. So what do we have here? We have 2 times pi cubed, 64 times 3. What is 64 times 3? It is 192. And then we have plus 1 over root 2. Multiply through the 2, so we have pi cubed. 192 divided by 2 is probably 96, plus 2 over root 2. This is an acceptable answer. Of course, your book's going to write it as pi cubed over 96 plus the square root of 2. It does look nicer because we do have this. We can rationalize the denominator and get just that. So you can verify that on your own. Both are acceptable answers. We use the fact that this was even to go ahead and use the property where we go 2 times this. This 2 times property would not work if these were not opposites. If it went from negative pi over 4 to 3 pi, then we could not do this to get the problem done. So there is problem number 2. Let's go do one more problem, because in your homework there will be some where the integrands are not even or odd. You'll say, well, what do I do? Well, what you can do on some of the problems, I think there's some where there's polynomials and there's some x to the 6th and x to the 5th plus x to the 5th, and what you want to do is see what these individual functions are. So the sine of 2x, of course we just affected the period on that, but it doesn't matter when you just affect the period on the sine, it's still going to be an odd graph. Okay, but what's happening over here? I mean, what is this? What I would do on this one is split the fraction. So I have integral from negative 10 to 10. We have sine 2x. When I split the fraction, I get x over x squared for the first part. So let me go ahead and write that. There's a minus there. This is x over x squared, and then we have minus 15x to the 6th over x squared dx. Okay, so this is the integral from negative 10 to 10. Sine 2x minus 1 over x. And then we have plus 15x to the 4th. Look, so if we're just looking, if we're looking at this whole thing, we might find that it's not going to be even and it's not going to be odd. But if you just look at these individual pieces, that guy's odd. This guy right here is also odd, because if you put a negative x in for x, you'll get the opposite function. This guy right here is even. So what I'm going to do with this integral is I'm going to break it up into 3 integrals. Negative 10 to 10, I've got my opposites there. This is sine 2x dx minus integral from negative 10 to 10, 1 over x dx plus integral from negative 10 to 10, 15x to the 4th dx. Okay, now we can see that this one is odd. This guy right here is also odd, that integrand. And this function right here, 15x to the 4th, that is even. So let's use some properties of integrals here. Oh, by the way, if you went to integrate sine 2x, find the antiderivative of that, we do not have the skills right now to do that. This would require a u substitution, and we'll get into that later in this chapter. So the integral from -10 to 10 of an odd function is 0. The integral from -10 to 10 of this odd function is also 0. Now I know some of you are like, well, isn't that the ln of the absolute value of... Yes, it is, but you don't need to do that because we're using the shortcut. Now, the integral from -10 to 10 of this even function is plus 2 times the integral from 0 to 10 of 15x to the 4th. So this is what it all comes down to. Can we do this? So let's move on here and see if we can. Well, I'm going to go ahead and take the antiderivative of 15x to the 4th. So I have the 2 outside. This is going to be x to the 5th over 5. And here's the 15. And this gets evaluated from 0 to 10. Now, what if I forgot to do these special properties here? Then you would have a lot more work. You would get the same results. Okay, let's go ahead and clean this up a little. This is going to give me 15 over 5 is 3. 3 times 2 is 6. X to the 5th. This gets evaluated from 0 to 10. So this is 6 times 10 to the 5th, and then minus 6 times 0 to the 5th. So that guy's out of there. This guy's a 0. So 10 to the 5th is a 1 with 5 zeros after it. Okay, I'm not going to put the 1 because I'm multiplying it by 6, so a 6 with 5 zeros after it. The answer is 600,000. So, you know, this is the kind of problem you get in your homework. They might not just give you a problem where the integrand is just an even or an odd function. They might make it so it is worth your while to split it up into more than one integral. So this completes the first part. There are kind of like 3 parts to this. Symmetry, and now average value. And here's the funny part about this. Is we've already done the average value of a function. So when your book asks for the average value of a function, they're really, if this is a velocity graph, they're really just asking for the average velocity. So just to put this back into our brains again, let's go ahead and figure out what the displacement is and then figure out what the average velocity is. The displacement happens to be the net area of your velocity graph in the time interval. And how do you get the net area? You get the net area by going like this, by taking the integral from 0 to 6 of t squared dt. So let's go ahead and do this calculation. We have t cubed over 3 evaluated from 0 to 6. You put 6 in there, you end up getting 216 divided by 3, that is like 72. You put 0 in there, you get 0. And so, what I'm ending up getting is 72 feet. So this is a bug on a number line, and from time 0 to time 6, he's displaced 72 feet. And that's 72 feet to the right from wherever he was originally at time 0. The 72 also represents the area, the net area of this graph from 0 to 6. And in this case, I usually draw that in blue because it's above the t-axis. I'm going to hold off on that. Now the average velocity. The average velocity, sometimes I call it AV, is gotten by going the displacement over the time. And so the displacement happens to be the thing we just found. This is 72 feet. Over the time, well, there's 6 seconds there, so this is 6 seconds. You do a little arithmetic there. 72 divided by 6, you end up getting 12 feet per second. Okay, now let's show you a connection to this. When we wrote displacement over time, the displacement was really this. 0 to 6 t squared dt. And then we put it over the time. The time is really 6 minus 0. Well, instead of putting it over that, I'm going to put it over here. So this is 6 minus 0. And so what a lot of books will say for the average value of a function is they'll say it's going to be 1 over b minus a. That's the length of the interval. Integral from a to b. And then they'll probably put an f of x in there, f of x dx. And so this is the average value of a function. Okay, so the average value of the function, let's just go ahead and see what that means. The average value of the function is 12. Okay, so where is 12? I'm going to go on the v-axis, which is the y-axis. It's about like a third. So here's 12 right here. And if I were to do this, I'm going to use green, and I were to draw a rectangle. Now my scaling is different, and the reason my scaling is different is because I wouldn't have enough room for the 36. So I make my scaling different if I don't have enough room. So let's look at the area of this. The area of that rectangle is what? It's 72. So basically this means this, and I'm going to actually write this out. If the bug was going at a constant 12 feet per second over the time interval, so I'll write that out. If the bug was going a constant 12 feet per second over the time interval 0 to 6. Now he wasn't. His velocity graph looks like that, but if he was, then he would have the same displacement that we found. His displacement would be 72. Another way of saying it with areas is the area of that green rectangle equals the original area under the curve from 0 to 6. And there was a reason I didn't do it in blue, because then you wouldn't have been able to see the green as well. So that's what it means. It means if the bug was going constant, that for the velocity, it would actually give you the same displacement as this displacement over the time interval. Okay, a few other things that we want to say is sometimes they call this average velocity, and we have not done it. They'll say, so here's the velocity. They'll call the average velocity v with a bar. Okay, and then maybe they would call this f with a bar. The other thing is, this might remind you of like when you are taking average values, or let's say you have a class of 30 students, and the students say, hey, what is the average on the test? What did the teacher do? The teacher added the 30 scores together and then divided by 30. Well, we can think about that as well. I mean, let's say we divided this curve in between 0 and 6 into 30 sub-intervals, and we put some points for the heights, and we wanted to know the average heights. We take those 30 heights, add them together, and divide by 30. But with the definite integral, now we have infinitely many rectangles. We have infinitely many heights on this curve from 0 to 6. And we are just finding the average value of infinitely many things, which is weird. We've never done this before. So infinitely many points, infinitely many heights in that time interval. The average height is 12. It's hard to believe that we're taking the average of infinitely many things. So let's get on to how the book is going to state this, and then we'll see an application of this too, because the applications are just amazing. You can actually see here where I did some whiteout work with the whiteout tape. That was a fun time. I guess I did something differently. So the average value, AV, which reminds you of average velocity. The average value of a function f over the interval a to b is 1 over b minus a, and I wrote this on the other page. So that's what it is. This, if you're a little confused, replace the f with a v and say that this right here is the average velocity. So in your homework, they're going to ask you to find the average value of the function on the interval 1 to 3. Draw a graph and indicate the average value. So what do they mean by that? Draw a graph and indicate the average value. That's how you indicate the average value with a rectangle. So we're going to do that. Let's go ahead and do this problem here. I'm going to go like this. So if you don't like this, think of this as a velocity graph. You can put a V there and say, hey, I'm just figuring out the average velocity, which is displacement over the time. But if you want to use this new formula gives you something called the average velocity, the average value, and it's going to be 1 over b minus a. 3 minus 1. The integral from 1 to 3 of 1 over x squared dx. Okay, so we have 1/2 out front. We're going to rewrite the integrand so it's something that we can take the antiderivative of. This is x to the negative 2 dx. And then what are we going to do? Well, then we're going to take the antiderivative. This is x to the, add 1 to that exponent, negative 1, all over negative 1, and then we have the 1/2 out front. This gets evaluated from 1 to 3. Need another piece of paper here. So it's really not that bad when they ask you to find the average value of a function. You're just multiplying the definite integral by 1 over the length of the interval. So this happens to be negative 1/2. You know what? Let's just go like this. So there's a negative there, and then that x goes down, so we have something that looks like that. This gets evaluated from 1 to 3. Okay, so I put 3 in there, and I end up getting negative 1 over 6. That's the first part. And then I'm going to subtract, and I'm going to put a 1 in there. I'm going to get negative 1 over 2. So this is negative 1/6 plus 1/2. That's negative 1/6 plus. We'll just keep going here. Negative 1/6 plus 3/6. That's what 1/2 is. And this gives me 2/6, which is 1/3. Which gives me the average value of the function, or the average velocity over the time interval. So we found the average value. It is this guy right here. So now they're asking us to draw the graph of 1 over x squared. The graph of 1 over x squared, you might remember what it looks like. You can plot points. It actually looks like this right here. So here's x and here's y. I'm going to actually, because my interval is from 1 to 3, I'm going to do a little close-up on this one, and we're going to draw the graph, and then we're going to draw a green rectangle that represents the average velocity. So let's do that. Okay, so we have this right here. So we're drawing the graph. I'm kind of tired today. Actually, probably going to make sure the camera is on. That would be bad. If I'm just sitting in my room doing the lecture to myself and not recording this, it would be terrible. Okay, so I have the point, let's see, 1, 2, 3. Let's just scale it off like this. And this is the graph of y equals 1 over x squared. So if I put 1 in for x, I get 1 over 1 squared for y, so that's 1. If I put 2 in for x, I get 1/4. Put 3 in for x, I get 1/9, which is like right on that tick mark. Okay, so I'm drawing this graph here, but I'm not going to draw the whole thing. And so I've got to turn the paper sideways so I can get a better feel for this. Okay, so it looks like that, and like that. Okay, I'm not going to draw the whole graph, I'm just drawing the part that I'm interested in. And so obviously this graph has an area under the curve from 1 to 3, and that area under the curve happens to be something, I think it's actually 2/3. So what am I doing? The average velocity is 1/3. So here is 1, and I'm going to go ahead and draw the rectangle. Here is 1/3. And what I'm going to do is I'll use the ruler again. Okay, so the area under this curve here pull out the big guns here, equals the area of this green rectangle. Okay, so that's what it is, and that's the average value, and that's how you represent the average value of your function. So there's all these heights here, like this guy, he's so tall, and this guy is so tall, and this guy is so tall. And how many points are there on this graph between 1 and 3? There's infinitely many, and we've measured them all. Okay, so there they all are. And you know, just like in a statistics class, to average something, you add them all up, add up all those heights, and then divide by the number of them. Well, there's infinitely many of them. So this is where calculus takes over. The average height of all those, think of those as little creatures there, and they're standing on the x-axis. The average height of them all is 1/3. So let's go ahead and do an application problem on this. Problem number 2. We're almost done with this section, by the way. This one is actually, I did steal this one from the book. I wanted to do a better one with temperature change, but those would require a U substitution, and we have not done that yet. So I'm going to go ahead and do this one. It says, the surface of a water wave is described by this. Okay, for negative pi less than or equal to x less than or equal to pi. So the graph looks like this, where y equals 0 corresponds to the trough of the wave. The trough is the lowest part of the wave between the crests. So that's what it looks like. Find the average height of the wave above the trough. So we're trying to find the average height of this, and that's what we're trying to do. So we have our formula where we can call this thing, if we like, f. And our formula for average value, 1 over b minus a, integral from a to b of the function f of x dx. This also happens to be the average velocity, and we've been dealing with that for a while. So let's just plug the numbers in there. Look at my A. So this is A here, and this is B. So I have 1 over B minus A. So B minus A. We integrate from negative pi to pi, and we put this function in 1 plus the cosine of x dx. Okay, so there's a few things going on here. The first thing to note is this right here. That right there is 1 over 2 pi. Okay, you can see that on the bottom. The second thing to note is we have opposites there, and this is just the shortcut. This guy right here is an even function. So you don't have to do this. You don't have to do what I'm about to do. I'm going to go like this. I'm going to say 1 over 2 pi. Okay. And then to evaluate this, I'm going to write this as 2 times the integral from 0 to pi of this even function, which happens to be 5 plus 5 cosine x dx. I guess there's the other part of my parenthesis that you can't see. It went off the paper. So a few things that we can do. We can cancel the 2's. We could also take a 5 out. Now you don't have to, but I'm going to. So this is really 5 over pi integral from 0 to pi of 1 plus the cosine of x dx. So we're going to find the average height of this wave. So this is 5 over pi. I'm going to take the antiderivative. The antiderivative of 1 is x. The antiderivative of the cosine is the sine. And this gets evaluated from 0 to pi. Well, I'm running out of space on this paper. I should have gone to another piece of paper. I put pi in there. I end up getting pi plus sine pi. Fundamental theorem of calculus says we go minus and then 0 in for x, 0 plus sine 0. So this gives me 5 over pi, and on the inside we have pi, sine of pi and the sine of 0, those are all 0. So I have 5 over pi times pi, the pi's cancel, I get 5. Now there were no units on here, so we can just say 5 is the average height of the wave above the trough. So that completes the application problem. Okay, our last problem is a problem we've already covered when we did bug 13. It's the mean value theorem. So the mean value theorem sometimes is stated a little differently when you're coming at it from the velocity function. It says that v is continuous on a closed interval AB. There is a number within that time interval such that the instantaneous velocity at that number equals the average velocity over the time interval. Now another way of saying that is we could say, or, so let me just put this in blue, v of c equals, what's the average velocity? It's 1 over, it's the average value, b minus a to b, v of t dt. Sometimes we'll say average velocity with a bar. Okay. Now remember, this is really the displacement divided by the time. So here's a problem in your homework. Now they're not saying this is velocity, but if it helps, you can label this as v if you want, v of t, and then put that as t. Find all the points in the interval 0 to 2 at which the function equals its average value. So I think the first thing you want to do is compute the function's average value, or another way of saying that is the average velocity. So you're just computing this right here. V equals, that's f bar equals 1 over b minus a, integral from a to b, f of x dx. And if you'd prefer to keep with the v's, you can, and change things out to v's and t's. Let's go ahead and do this. This is 1 over 2 minus 0, integral from 0 to 2. Our function is 1 minus x to the 4th over 4 dx. So what do we have here? We have 1/2, and now I'm going to go ahead and take the antiderivative of 1, which is x Actually, I think I wrote the problem down wrong. Okay, I've just noticed that. So you'll just have to excuse my whiteout. This in the book actually said, not that we couldn't do that problem, there was actually a squared there. So sorry for the inconvenience or the trauma. There we go. I just peered over at the book and I realized, wait a minute, there's a 2 there. Okay, so it didn't really affect anything yet. That's from me copying the problem down wrong. So the antiderivative of of 1 is x. The antiderivative of x squared over 4 is going to be, so we have minus x cubed over 3, but 3 times 4 is 12. This gets evaluated from 0 to 2. Okay, let's finish up this problem. I was eating potato chips before this, and I think I got some salt in my throat. So, if you hear me cough, excuse me, it's not the coronavirus, it's the salt sodium virus. Okay, I'm going to go ahead and put some numbers in here. So 1/2. So let's put 2 in there. When we put 2 in there, we end up getting 2 minus. So this is going to be 8/12, which is 2/3. Fundamental theorem of calculus says minus, and then put 0 into this function, which is just 0 minus 0. And so what is 2 minus 2/3? Let's go ahead and write that out there. 2 minus 2/3 is 6/3 minus 2/3, 4/3. We end up getting 2/3 for our average value of the function, or if you like, average velocity. Okay, so they're trying to say, okay, the mean value theorem says that there is a time within this time interval where the velocity has a value that is 2/3. So what are we going to do with this? So remember, this is our velocity function right here. If you could replace this with v of t and put a t there, that there is some time where this guy right here, where the velocity is 2/3. So I'm going to put that in for f. So I have 1 minus x squared over 4. And now I have an equation to solve. I'm going to multiply both sides of that equation by the LCD of 12. So I end up getting 8 equals 12 minus 3x squared. And then this gives me 3x squared equals 4x squared equals 4/3. X equals plus or minus the square root of 4/3. X equals plus or minus 2/√3. Now, these give me, if you put this on your calculator, you get plus or minus 1.15. Okay, so I rounded it. And our time interval, was 0 to 2. So it says find all points within this, or times within this time interval at which the function equals its average value. Well, you're not going to go with the negative because it's not in that time interval. You're going to say, the answer happens to be, so here's the answer. It happens to be 2/√3, which is 1.15. And so basically that is a time. So the time is 1.15. And if this was the velocity function, you would say the instantaneous velocity at 1.15 equals the average velocity over that time interval, the average velocity over that time interval being 2/3. Now, we could draw this graph again here. We haven't drawn a graph yet, but the graph is okay, so I'll do this right this time. Make sure the camera's still running. Y equals, what is it? 1 minus x squared over 4, which is an upside down parabola, a little wider and shifted up one, so it looks like this. You can find the x-intercepts. I think the x-intercepts are 2 and -2. Our time interval we're interested in is this right here, from 0 to 2. So we have found an average value of the function. The average value of that function was 2/3. So this goes up to 1. 2/3 is right here. And so in the other problems, they asked us to draw that rectangle, and the area of that green rectangle is equal to the area under the curve. But watch what we just found. Look at this point right here, which on the x-axis happens to be approximately 1.15. So we found the time within that time interval that gives us the same value as the average value, and that's what the mean value theorem says. Now, looking at it from the derivative graph or the velocity graph, it's so much different, the mean value theorem, than it is when you're looking at it from the original position function, because then you're just looking at slopes and you're saying we can find the slope of the average velocity equals a slope of a tangent line within that time interval. So it just blows your brain when you just look at the mean value theorem from both ways. But I remember the mean value theorem says the average velocity over a time interval. No, what it says is there is a number within the time interval, a time within the time interval, such that the average velocity in that time interval equals the instantaneous velocity at that time within the time interval. And there could be more than one time in the time interval. Anyway, this concludes our lecture on 5.4. Do your homework and have a good day.